Hi, my name is Andrew Rashid, and I'm the team lead for Cal Poly Pomona's AUVSI competition team. I am of the class 2020, and I've been on the team for 2 years now. I've also had 2 years of experience working with UAS technologies, specifically in hardware and piloting. My role as team lead is to manage both the hardware and software teams. On the flight line, I'll be assuming the role as a safety pilot. Now the other members of the team will introduce themselves.
My name is Luis Rodriguez. I'll be graduating this June in aerospace engineering. This is my 3rd year on the AUVSI competition team. My experience includes the AUVSI team as well as starting the UAS club last year, where we assist various unmanned autonomous vehicle projects in flight test preparation, ground station setup, and flight testing. My role on the team is Vice President and Hardware Lead, where I oversee all the modifications done to the flight vehicle. And my role on the flight line will be assisting the safety pilot as the safety observer.
So, my name is Crystal Ramirez. I am class of 2017 aerospace engineer. This is my first year participating in the AUVSI team. The previous years I've been involved more with rocket designs. Throughout the year I've been in charge of CADing and hardware modification. For the competition I will be involved in helping set up, and I'll be an antenna tracker operator.
I'm Miguel Lopez, aerospace engineering, class of 2017. This is my first year on the team, and my role is to do the CAD modeling and help with the hardware on the flight vehicle. On the flight line, I will be preparing the flight vehicle and managing its power subsystem.
My name is Kyle Winterer, class of 2017, graduating this year in June. I've been on the team for 3 years, and I have a lot of experience with UAVs, both in multi-rotors and fixed wings. My role on the team is the software lead. I monitor the programming done for this project. On the flight line, I'll be operating the ground station program, which is Mission Planner, and I will be operating the interoperability program.
My name is Alexander Ray, aerospace engineering major, graduating class of 2018. This is my first year working on the competition team and my first year working with UAS technology. My role on the team is to develop an algorithm for obstacle avoidance, and on the flight line I will be a ground station operator.
My name is Bogdan Pugac. I'm part of the Electrical and Computer Engineering Department, class of 2017. I've been on the team for about 3 years now. My experience is with flight software, computer vision, and artificial intelligence. I'm in charge of the object detection, classification, and localization software. On the flight line, I'll be operating the imaging computers.
Thomas Fergus, aerospace engineering. I'll be in the graduating class of 2018. This will be my 2nd year on the SUAS AUVSI competition. Over the past 2 years, I've been working specifically on the software side of unmanned autonomous systems. This year, I was working particularly on the drop code mechanisms and the software. On the flight line, I will be the assistant ground station manager.
Here is the mechanical overview for our vehicle. Our vehicle is an electric hexacopter from DJI, whose structure is composed of a carbon fiber frame. We have a 2-axis gimbal used to stabilize the camera on the vehicle during flight. We also have a water bottle drop mechanism that utilizes a servo in order to release the water bottle.
The main battery for our hexacopter is a 16,000 milliamp hour 6-cell LiPo that lasts 17 minutes in flight. There are two 2200 milliamp hour 3-cell LiPos. The first 3-cell powers the Pixoc autopilot system and the HDMI to Ethernet adapter. The second LiPo powers the 2-axis brushless gimbal and the Bullet M5 antenna system. Both of these 3-cell LiPos last over an hour.
Cal Poly Pomona AUVSI SUAS team use a modified version of Mission Planner, seen here, for completing the tasks given in the AUVSI SUAS competition. The tasks include interoperability, bottle drop, and collision avoidance. The collisions provided from the server are available on screen here to show the purple stationary obstacles and yellow moving obstacles. Images can be reviewed using this browser to browse images already currently on the server. Any of these characteristics can be changed at any time using these buttons and uploaded using the upload button. Tasks such as obstacle avoidance and bottle drop use MATLAB and calculate the results. Visual Studio and MATLAB provide support for running MATLAB code from a C# application. We take advantage of this in order to calculate our bottle drop location and as well as our collision avoidance directions. The image processing system also uses MATLAB in order to find the targets on the ground and process them. This year, the Cal Poly Pomona AUVSI SUAS team will attempt the autonomous flight, stationary obstacle avoidance, object detection, classification and localization, and the air delivery task. We will not, however, be attempting the moving obstacle avoidance task. We are 100% confident in our autonomous flight performance, including autonomous takeoff and landings, as well as waypoint path flying. We are 100% confident in our stationary obstacle avoidance task, since our stationary avoidance is based on our waypoint accuracy. We are 100% confident in our system's ability to autonomously submit targets. However, we are only 50% confident in the performance of the autonomous target detection, classification, and localization task. Although we are 100% confident in our ability to submit targets manually and find targets manually. We are 90% confident in our air delivery task. We are able to deliver the target, but the accuracy needs further testing for a higher score. For testing our code and other various tasks, we first test our code in separate projects in Visual Studio or MATLAB. Those tasks would include collision avoidance, bottle drop, and target detection, and also interoperability. Each of those tasks are then added to the main Mission Planner program, the modified version of Mission Planner we are currently using. We test the core functionality to make sure that it works on the ground before we fly. Then we test the code in a flight test with our test platform, a 3DR hexacopter. Because this can be flown low and slow, and also because of its size, we prefer to use this test platform for safety. We can then verify that once the code can be run safely and can perform correctly, we can test it on our mission platform, the DJI S900 hexacopter.
We have conducted a total of 14 autonomous flights. Approximately 75% of our flights were in manual mode. PIDs were set to conservative values for autonomous flight. A lidar light sensor is used for autonomous takeoffs and landings. The lidar light was calibrated for ground level. The lidar light is also tested before each and every flight.
For testing waypoint accuracy, we used 4-foot radius on all of our search grid waypoints, as can be seen from here. This is an example search grid what we use when we test. And here is a telemetry log from the past where you can see the trace made from the flight on our Hexa rotor. We have never missed a waypoint in any of our flight tests, as it is programmed into our autopilot to hit all those waypoints in the radius. And due to the fact that it's a multi-rotor, we are confident that we won't miss any waypoints, unlike a fixed wing vehicle which may fly past a waypoint without being able to meet it.
The stationary obstacle avoidance algorithm takes in a set of waypoints, obstacles, and boundary area points and outputs a set of waypoints for the vehicle to maneuver through. The longitude and latitude coordinates of the waypoints, obstacles, and boundary points are converted into a relative coordinate system. The algorithm first checks to make sure that there are no waypoints placed within any objects. If so, it shifts them to a nearby point that's outside the object's radius, but within the boundary area. Next, the algorithm iterates through pairs of waypoints looking for any points of collision. If there are any collisions, the algorithm takes the nearest colliding object and finds a point to maneuver around it. The set of waypoints is then updated with the new waypoint, and the algorithm checks for any collisions due to the new waypoint. If there are more collisions, more waypoints are generated to path around the obstacles. When there are no more detected collisions, the algorithm moves on to the next pair of waypoints. All of the waypoints are stored within a list, and after all waypoints have been prepared, it converts them back into longitude and latitude coordinates and feeds them to the vehicle. Testing of the stationary obstacle avoidance code was done by plotting the waypoints, obstacles, and boundary area on MATLAB. The initial and corrected flight paths can be visually represented, and any collisions can be shown. The algorithm gives a 10-foot safety radius to the vehicle in case the vehicle overshoots its intended flight path.
For the camera system, the camera's focal length and ground track area was initially tested on the ground at a distance of 200 feet. The current focal length is 70 millimeters, but is still being optimized to minimize search time while maintaining high image resolution. Handmade targets and license plates were used to test in-flight recording and ensure high-quality images were streamed down to the ground with smaller than competition-sized targets.
The software for object detection, classification, and localization was tested with a testing data set and with real-world flight data based on objects created by the team. The testing data set used similar images as the ones used for training, and it had an accuracy of about 88%. The software was then tested during flight using objects created by the team. Different focal lengths and image filters were used to determine the optimal settings. The real-world accuracy was 62%, and additional testing is ongoing with a goal of achieving 80% accuracy in real-world tests. Additional testing was done on the software used for the manual portion of the task. The goal of testing was to make sure that the code would continue to run smoothly if the link is lost and reestablished. The code is expected to be stable throughout the duration of the flight. Localization is done by determining the region of the target and extrapolating the GPS location based on the focal length, image size, and GPS position of the center of the image. The error from this process is minimal because of the captured area of the image at only about 400 square feet.
We have tested the air delivery code 21 times now, and have determined that the bottle has a 76% chance of surviving. However, with our final design iteration, the bottle has yet to break. Using MATLAB to optimize the drop location, the bottle is only offset by 30 feet on average from the target.
Full mission tests have been conducted to ensure that our targeted objectives are met. We are capable of autonomous flight with waypoint navigation, air delivery, and imaging. The UAS hit all the waypoints within a 4-foot radius 100% of the time. The water bottle averaged 30 feet from the target and did not break during the full mission tests. The imaging software was able to detect targets with a 62% accuracy. A flaw that we found during full mission tests is that we will need to land halfway through the mission in order to change motor batteries due to the aircraft's limited flight time and range. Collision avoidance has not yet been directly tested in the air. The concept in which waypoints are rewritten while in autonomous mode has been tested in flight. This concept is a mechanism we plan to use for avoiding obstacles. Overall, the full mission tests determine that we are able to complete our targeted objectives.
The maximum percentage that we will be able to achieve is 99.6% for the flight demonstration. This number comes from us not being able to complete off-axis target search. The score we expect to receive is 84.6%. This comes from the possibility of moving obstacles not working correctly, bottle dropping off by 30 feet, and the geolocation off by 75 feet in addition to the maximum percentage.